No, no, look, I mean, I have no portions to finish. I want you all to go away with at least, there's no point in doing some advanced stuff if the basics are not ready. Okay, okay, fine. I can see that there are some faces who want to say yes and are not willing to speak out. So let me give a very quick review. So before I start the review on electrodynamics, I actually wanted to stop with the Lorentz group and transformations, but I found that I need one more property. So let me go over what I said in the last class. So we were talking about tensors and vectors. So 4 vectors and 4 tensors, and tensors. So we had defined, I hope all of you remember, contravariant and covariant vectors depending on their transformation properties, right? So let us see who remembers. So if I put, I think I called this A and I called that B, let me not change the notation. So this was called A and this was called B. So this is the primed variables and they will be related to the unprimed variables. So what will be the, so let us put all the, now you have to tell me what is coming where, right? So let's look at A prime alpha. If it's contravariant, what will be at the top? X prime alpha, very nice. So this bottom will, let's just call it beta. So once this is beta, this will also be beta. And you remember that when we have repeated indices, they are summed over, right? So that means A0 will be related to dx prime 0 by d0 plus dx prime 0 by dx1 plus dx prime 0 by dx2 plus dx prime 0 by dx3. I hope this is very clear what we mean by repeated indices. It's not just one quantity, it's a whole series of 4 terms, right? Okay, so what happens with the covariant vector? So x is on the top, x prime comes below. The indices don't change, right? Beta is below. So alpha is on the top, beta is below. So, okay? Huh? Oh, sorry, yeah, you're absolutely right. It has to be B beta. Thank you. Yeah, there is no transformation that takes A to B, not Lorentz transformation. So, okay, and the tensor we had defined. So you keep going this way. You have series of indices, right? I called it F alpha beta. So the primed variable will have two indices to lower it. So this will be, because it's above, it will be, this will be prime, this will be prime, this will be alpha, this will be beta. Let's call this gamma and delta. So this will be gamma and delta. So I guess you can do the covariant thing as well, right? I'm not going to write it all. What happens if I didn't do this? Yeah, only one variable will be. That's your choice, right? You can do whatever you want, but this will not be the same f variable because the Lorentz transformation, if this is prime and unprime refer to a Lorentz transformation, then of course this is incomplete. But as tensors, you can always define contravariant and covariant vectors like that. And then I defined a B dot A as either B alpha A alpha or lower alpha A upper alpha. And that was because, if you remember, I actually showed you that I have a special object called the metric tensor G alpha beta, which is the same as G lower alpha beta, which you can simply check from this definition. Check that the G upper alpha beta and G lower alpha beta are the same, and this is equal to the diagonal matrix of 1, minus 1, minus 1, minus 1. This is because we have taken x alpha to be Ct xyz. Some books will define x alpha as xyz comma Ct. Then in that case you will have the metric tensor will have minus 1 plus 1 plus 1 plus 1, but it's your choice. It won't make any difference to the physics, okay, as long as you know what you're doing and you have a consistent set of definitions. So because of this, I can use G alpha beta or G alpha beta. So G alpha beta will raise a covariant vector and G lower alpha beta will lower a contravariant vector. So if I make X alpha, G alpha beta, so alpha is summed over, beta is not. So what should I expect on the right hand side? I'll get X covariant beta. Now you can see the notation helps. By putting the covariant indices on the bottom and the contravariant indices on the top, you can see that for a proper dot product, which is a scalar, which means it's invariant under Lorentz transformations, you can check that this will be invariant under, what does this give you? Do you remember? If I take X alpha, what does it give me? X alpha covariant times X alpha contravariant will give me ds squared, right? S squared, which is the invariant distance between x1 and x2, right? Or 0 and x in this case, right? Because it is an invariant, you can see that if one index is above and the other is below, and if this index is below, the other side index also has to be below. So you simply have to make sure that you match these indices. So the number of indices above on the left hand side must be equal to the number of indices above on the right hand side, okay? And you can immediately see therefore that X beta, it's very trivial because it gets multiplied, this is diagonal, right? So it will get multiplied by 1 for CT and minus 1 for the others. So it will be CT times minus X minus Y minus Z. So in general, if I label the upper index X alpha, this is a repeat of the last time as X naught, X1, X2, X3, and the lower index by X naught, X1, X2, X3, then I will have X naught is equal to X naught. So I'll never actually worry about the 0 component, but X1 will be minus X1 and so on, right? You can see that, right? It's trivial. This is upper X1, this is lower X1. So when we use the notation 3 coordinates, X, Y, Z for the 3 vector component of the 4 vector, we are referring here to the contravariant part. X, Y, Z belongs to the contravariant set. Minus X minus Y minus Z will belong to the covariant set, okay? Is this clear? Because there is a little hitch here. You think of writing suppose I want to convert, like yesterday we did, right? We wanted to write d by dt prime in terms of d by dt, right? So what did we write? D by dt prime is d by dt into dt by dt prime. That is the chain rule. So suppose I write the chain rule for, so d by dx prime alpha. I am not doing a Lorentz transformation here, but I want to simply rewrite this derivative in terms of d by dx, not d by dx prime, using the chain rule. So how will I do it? This will be equal to d by dx alpha, or not alpha, what index will I use? Let's call it beta, because I don't know that it will be the same, times dx beta by dx prime alpha, right? It is exactly like d by dt prime is d by dt into dt by dt prime, right? And there are 4 indices here, right? So let me just actually write it interchange. This is just a number, right? So I am getting this from the chain rule. But then you look at this. What does it look like? Does it look like A or does it look like B? Huh? It looks like B, right? So that means naturally by construction, the derivative is a covariant object. Those of you who are in MSc may have heard of covariant derivatives, right? They are always covariant derivatives because they transform like a covariant vector, right? Is it clear? So this, I will therefore give the symbol d alpha, lower, and then therefore I will write d alpha lower is d by dx. See, it was related to d by dx upper, always the x's are upper x's, right? d by dx1, d by dx2, d by, so this is what I missed out yesterday, it's very important. So you can see that I can call this x0 is c dt, right? So this is 1 by c d by dt, and what is this remaining part? What are upper x1, x2, x3? So what is d by dx, d by dz vector? Huh? It's a vector, right? It's a 3 vector. d by dx, d by dy, d by dz. Gradient, very nice. This is a gradient vector, right? Is it clear? I hope you have seen all these before, right? Gradient, curl, everything. You can't write Maxwell's equations without gradient and curl, right? So, fine. So what will happen with the upper alpha? Now I don't have to compute anything anymore. You now know that x naught will remain the same and this will become minus del, right? And immediately you know in quantum mechanics that del operator is related to the momentum operator. So you will see that unlike the space coordinate, the momentum operator, the positive valued momentum operator will be covariant and the P upper alpha will be contravariant, right? So this is something that is different from what you usually have. I'll give you an example of the continuity equation. You have seen the continuity equation. If I have a charge distribution rho, this is a charge density and a current density J, then the continuity equation can be written as d rho by dt plus del dot J equal to 0, right? I hope everyone has seen the continuity equation. What does this mean? That if I have some volume, because this is all densities, right? I have some volume in my mind and whatever charge is changing in this volume over time is actually going out as a current flow, right? This is true whether it is electrodynamics or whether you are talking about water flowing, right? Sorry? Probability, yeah. So the continuity equations occur everywhere. It's just a law of conservation of whatever, this is the current density, it could be the flow density, it could be probability density, anything, right? So now you can see that here I have, let me put, that side is anyway 0. Now you look at the del operator and you can see something over here. So if I define now another 4 vector which is j alpha, which is rho comma vector. Okay, whenever you cannot see my vector sign, I put the arrow, otherwise I just put underline for vector. So don't get confused, they are the same thing. If I think that you cannot see it, I actually put the vector form. So if I define the 4 vector current J and I already have the 4 vector del, then you can see that equation is nothing but d alpha j alpha equal to 0. Is it clear? Can you see that? So the minus sign, minus of the minus sign becomes plus, right? Because that becomes the lower component is plus del and the other guy would be also plus. So this bookkeeping really helps you in making sure that you get your signs right. That is the main reason you write everything in 4 vectors. You can see that this is now manifestly invariant, right? Alpha alpha, now you know that they're proper 4 vectors. So that means d alpha, j alpha is a scalar and the right hand side is a scalar. So you can see this is manifestly Lorentz invariant. So by just reconstructing everything in terms of manifestly invariant quantities, you will be able to say that yes, electrodynamics actually is invariant under Lorentz transformation. You don't have to do those horrible Lorentz transformations and then go wrong in the factors and the signs and things like that. So that is what we are trying to do now. So this is one thing I wanted to tell you, that you have to be a little careful with del. The other thing I want to tell you is, which is something that I will use. So it is a little bit mathematical right now, but as I said, I'll need that a little later, so I might as well do it when I'm talking about Lorentz transformations, is we are now writing some x prime in terms of x, and x prime is a 4 vector, x is a 4 vector. So I can now think of a matrix representation where my x prime alpha is a 4 vector. So its x prime is this, okay, and I can write x prime therefore is related to x through some matrix. This is your Lorentz transformation matrix. So for example, it will have gamma times, so this will be x0 prime in terms of x0 will be, so gamma times t minus vx by c squared, whatever. So all those entry elements you will be able to write, okay. Fine, you understand this, right? So now that I have a matrix, I can immediately talk about x transpose. So what will x transpose be? X transpose will be a row vector. So I can now do matrix multiplication, right? So what do I mean by x alpha, x alpha? So when I say x alpha, I mean row times a column, which is simply a number, right? So how do I convert the column into a row? By multiplying by g alpha beta, right? So I can nominally call this scalar product as x comma x with a g in front of either this one or a g in front of, I can do anything, right? I mean, because I can have x upper alpha, x lower alpha, whatever, so I can simply write this as, so any dot product, any dot, not just x, let me just put some a and b, dot product of a and b, I can write as this, where G is the matrix of G alpha beta, right, which is simply diagonal 1 minus 1 minus 1 minus 1. Now why am I doing all this? So what is the special property of a Lorentz transformation? That x alpha is an invariant, right? So all the Lorentz transformations are under the constraint that is, which is actually just s squared, right, is an invariant. So now let me write, so x prime is equal to, what have I given it as? I have given it a name A. So A is a 4 by 4 dimensional matrix, I hope you can see that, right? If this is 4, then this is a 4 by 4 matrix, okay. So now I know that under the constraint, what is the constraint? That x prime gx prime is equal to xgx. So how do I write, how do I multiply this? I have to convert one into a row. So I can write it as x prime transpose gx prime is equal to x transpose gx. So now I can, x transpose is simply this row matrix, right? That's why I defined it. But what is x prime? X prime is ax, right? And this is ax transpose. What is the formula for AB whole transpose? So this will give me x transpose A transpose G times A times x, and this has to be x transpose G times x. So what can I tell you, what can you all tell looking at the board? Very nice, somebody is awake. And there are many more things you can do with it. I am sorry I cannot, in 5 lectures tell you everything about everything. I don't even know everything about everything. I just want to take determinant on both sides. What is the property of product of matrices? Determinant? Huh? Very nice, it can be multiplied. So determinant of ABC is determinant A into determinant B into determinant C. And what is determinant of A tilde and determinant of A? No, not one, they are not inverse. They are the same. If you transpose a matrix, its determinant remains the same. A is a square matrix, remember, okay? Fine, so determinant of A transpose, you're looking at it like this, you're looking at it like this, whether it's rows or columns, you don't care, right? So this is the same as determinant of G times determinant of A squared is equal to determinant of G. So what can you say about determinant of A? 1. Very nice. I can't see who said that, plus or minus 1. Okay. Now you can check by saying you can use x prime is the reflection of x, or x prime is the time reflection of x. When I say x, I mean 4-dimensional x space. So when I say time reflection, x0 prime goes to minus x0, right? Or the space reflection when xyz goes to minus xyz, right? You can try all such things and you will find that they all will have determinant of the transformation, because you can write the A, right, and find its determinant. It's very easy to do that. And you will find that those constitute the determinant A minus 1 subset. But the determinant A plus 1 subset are what are called proper Lorentz transforms. So this is what I want. So plus 1 are called proper Lorentz transforms, and they will include the boosts that we are talking about. Boost means transformation from one inertial frame to another inertial frame, and rotations also. Okay. So the Lorentz group will contain both determinant A plus 1 and minus 1, those who know a group theory, otherwise just forget it. And determinant A plus 1 is what we will use sometime, either most likely tomorrow. Okay, so please remember it till tomorrow. But once I am doing this, I wanted to just finish this part of things. Is it okay? So no, let's not say more about it. I think you can always read more, right? You don't need me to tell you this. Okay. So before I give a brief review of Maxwell's equations, let us try to guess what are the 4 vectors in the theory, because I am claiming now that I can write a manifestly Lorentz covariant Maxwell's equations, one set at least, and therefore I should be able to write everything in terms of 4 vectors, right? Then I know that it's manifestly Lorentz invariant. That's what I want to show. So already we have so many 4 vectors, right? So let us see what all we have. We have x alpha, right? Then we, of course, for tensors we found g alpha beta. Then what else did we find? Huh? 4 momentum. 4 momentum. So we had first started with u alpha, I hope you remember. In yesterday's class we showed that the velocities are not, c comma u does not form a proper 4 vector, but gamma times c comma u forms a 4 vector, right? Right, so this, and m times that will give you the 4 vector p. Now you can see that you can also write p in terms of d by dx, but you remember that, right? We wrote d by d tau, right? So the m d by d tau of this u alpha will give you p. So we also saw, let me write it, so this can also be written as right. What is p alpha? P alpha? Sorry, now I have to somewhere put pc. Sorry, the c equal to 1, sometimes when you put back the c's, yeah, this is correct, yeah. So what is p alpha? P dot p? It has to be an invariant, right?
Isn't it E by C?
Huh?
E by C in the 4 momentum.
Doesn't matter, you choose. Somewhere the dimensions have to be the same, right? Pc has dimension of energy. If I put E by C, then P, the E by C has dimensions of P. Depends on your definition, no? Who cares? I mean, it's a constant. C is a constant. It won't affect the transformation properties of that vector. Yeah. So what is P squared? Very nice. So is equal to, so this is, I said yesterday was, because I put the C here, it will be C power 4. If I had put the C here, it would have been m squared C squared. Please put the C's back correctly. The units of energy are E, PC and mc squared. So I want you to also do as homework, please make sure those are the units of energy. Make sure that mc squared has units of energy. Make sure that PC has units of energy. PC you know because energy of the photon is PC. So you know that has units of energy. E of course is energy. And you make sure that mc squared has units of energy. Right? So this units and dimensions are very important. If you know how to deal with units and dimensions, you can guess a lot of answers just by looking at the dimensionality of the problem, right? Okay, so where were we? Yeah, so 4 vectors. So okay, so this comes, so this is also equal to m times u alpha, right? What are the other vectors? 4 vectors we know? Huh? We just wrote j alpha, very nice. So j alpha is again rho and j. So you can either put 1 by c here or you can put 0, one of the two places. It's your choice, right? So what is, this is not enough for electrodynamics, right? There are more things in electrodynamics. Huh? Electric and magnetic field. How can I make a 4 vector of electric and magnetic field? Right? See, what all are there? I have to have all these quantities, right? So I need to write, this is a 3 vector. I need to find some partner of these 3 vectors to find a 4 vector, right? And it will turn out that actually you cannot do it. Okay? And actually it will turn out that E and B will be components of a tensor. You remember F alpha beta I introduced, right? So actually E and B are elements of a single second rank tensor which is called F alpha beta. And the elements of F alpha beta will be E and B. How many components are there in F alpha beta? 16, right? It's a 4 by 4 matrix, right? Alpha goes from 0 to 3, beta goes from 0 to 3. You can think of a matrix as 4 by 4 matrix, right? Right? But I now say that this is an antisymmetric tensor. I'll show you later why. Suppose it's an antisymmetric tensor. Then can you tell me how many elements are there? Huh? Don't give me formulae, no? I mean, substitute and tell me. Right? What is an antisymmetric? What are the diagonal elements of an antisymmetric tensor? 0, very nice. So I have a 0, 0. So we have already solved for 4 elements, right? What else do you know about antisymmetric tensor? So you have, what is left over here? 1, 2, 3, 4, 5, 6, right? What do you know about an antisymmetric tensor? What is negative? Transpose is negative. So where is the transpose? Suppose this is the 0, 0 element, this is the 0, 1 element, right? So what can I say? If I know 0, 1 element, what else will I know? 1, what will be 1, 0? Very nice. So how many elements are there? 12, no, you just told me that these are the same, right? With a minus sign. So how many elements are there? 6. And how many elements are there of E and B? 3 E's and 3 B's. This is not higher mathematics, right? So there are 6 components of E and B fields, and those will become the 6 elements of this antisymmetric second rank F alpha beta. And we will get there. We will see how we can actually construct the F alpha beta which contains this E and B fields. Then we will be able to rewrite Maxwell's equations in terms of F alpha beta. Okay? What else have you studied apart from E and B fields in electromagnetism? I will just go give a quick overview, but this will just tell me like how much you remember of the stuff. Huh? What else is there? That's all. I can't hear. Who was it who was saying something? Yeah? Potentials, very nice, that's what I was looking for. So what are the potentials you know about? Vector and scalar. So boom, can you put them together? How will you put them together in the 4 vector? So can I call it A alpha? I think, okay, fine, I won't swear to it, okay. Is it clear? So if you see a potential which is scalar and a potential which is vector, you hope that they will transform like a 4 vector. So all these, by the way, you have to check. You have to check the transformations. But once you write it all in terms of completely covariate notation, it will become extremely trivial to check these things. So I am not going to check it right now. We will do the simpler version later. So these are the kind of quantities that are appearing in your magnetic field and electric field as different combinations. And now you can understand what you would have learned in electromagnetism is that once you have a moving charge, so when I have a static charge, that's a whole chapter called electrostatics, and its electric field is Q by R squared. But once that charge starts moving, you know that it generates a magnetic field. And then Faraday found that if I have a changing magnetic field, then it generates an EMF, which then therefore gives rise to an electric field, right? So you can see why that happens, because the transformations of F alpha beta, now you can see what will happen to F alpha beta prime. How will I write F alpha beta prime? Dx alpha prime by dx gamma, dx beta prime by dx gamma, F beta gamma, right? So it will mix up all the elements. So the E field will mix up with E and B field, right? And therefore it turns out that when you move from one frame to another, if I am in the frame where the charge is at rest, I have pure electric field. When I go to the frame where the charge is moving, then it immediately generates a magnetic field that comes out naturally by looking at Lorentz transformations. Is it clear? So the reason we are doing all this, so before I start writing all this and you wonder where I am going, what we want to do is actually rewrite it in these terms so that we will have a very good handle on looking at these kinds of transformations, and we will be better able to understand how these electric and magnetic fields so called mix, and moving charges can give you magnetic fields and moving magnets can give you electric fields and so on, okay. Fine, I don't need to wrap it, okay. So now let me do maybe. Let's see if I missed anything. No, I don't want to do all this. Yeah, you can do lots of things, but I don't want to do it. Okay. Maybe before I proceed, I don't know where exactly I will use this, but rho over here, right? This has a very fundamental implication. If I take a charge density which is localized in some small space and I integrate it over all space, so I make sure that I cover all the places where the charge density is distributed, what will I get? Total charge, right? So rho d cubed x. So provided I haven't missed anything, is just the total charge q, right? Now what we just say is that Q is a Lorentz invariant. See, we don't have any transformation laws of Q, okay. The charge is the charge. In whatever frame I look at it, you can just think of, suppose I have a bunch of electrons here, then some 10 power minus 19 coulombs, so many of them are there, and in whichever frame I look at it, they are 10 power minus 19 coulombs, right? So the charge is an invariant of the Lorentz transformation, and therefore this left hand side rho d cubed x is an invariant of the transformation. But then you see that rho d cubed x looks similar to a 4-dimensional volume of our space time, which I can write as the usual 3-dimensional volume times the volume due to x naught, right? So this whole song and dance about determinant A being 1 was that if I transform d4x to d4x prime, then it will transform to dx naught prime into d cubed x prime, okay. Now let us assume that only dx prime changes and dy and dz are the same. Again I am doing the simple case. Now you remember If you want, you can put all your equations. You know how x prime looks in terms of x and y, t prime looks in terms of t. You don't have to do all that. Just remember that time dilates. Time dilates by how much? Gamma means gamma in the numerator or denominator? Right? And length contracts by how much? And so what can you say about this? This is an invariant. Okay, this is now just my hand waving argument. You can write this when you write a transformation from d4x prime to d4x. You can write d4x prime is equal to the Jacobian of the transformation times d4x. I hope you have seen Jacobian in 3 dimensions. If I take xy and replace it by r theta, then I get a Jacobian of the transformation, which will be x naught prime, x2 prime, etc. divided by x naught, x2. So this is just the determinant of this matrix, right? And this will become the determinant of, so I am not going to do it, you can ask someone in the tutorial to do this. This becomes determinant of A times d4x, and therefore I have just shown you that for a proper Lorentz transformation, determinant A is plus 1, and therefore d4x prime is equal to d4x, okay? So since here I have explicitly used the proper Lorentz transformation, I already got plus 1, but in general you can show that this comes out to be plus 1 for proper Lorentz transformations. So now that brings us back to this. I can therefore write d4x as dx naught times d cubed x, and I know that this is an invariant volume. This is an invariant. This, by virtue of being a charge, is invariant, and therefore you can see that rho has to transform like the time component of a 4 vector. Is it clear? And this is why we are putting, this is why we put rho as the time component of the 4 vector, okay. So such insights are many. This is just one example. There is something about J, but I think I will skip it. There is something about A, I think I will skip it. Okay, so let me just do this review first, because we have talked about so many quantities. Let us just, okay, do a review and then we will continue. Okay. Because I just want to set the notation, otherwise you will not know what I am trying to do. When I rewrite the Maxwell's equations in 4 vector form, at least you should know them, right? So this is all right, right? There are no questions on this? It's all okay? Fine. So here is a brief review. Well, anybody's, but ultimately Maxwell's electrodynamics, right? Okay, where do I start from? Okay, where will we start from? Tell me, what is it you know about Maxwell's electrodynamics? Let's start with electrostatics. What do you know about electrostatics? Huh? Gauss law. Okay. You don't want to start with Coulomb law? I hope you know that Coulomb law is the physical law. Gauss law, what is the difference between Coulomb law and Gauss law? Okay, tell me what is Gauss law, tell me. What is Gauss law? Huh? One person. See, you must understand, I can't hear from this side. No, I don't want words. Just give me some equation, right?
Then integral E dot dA,
Huh?
integral E dot dA is equal to Q by epsilon naught. Okay.
Okay, you want epsilon. Okay, fine. Okay, fine. So let me start with, I will come to your Q by epsilon naught because I want to write so my rho d cubed x is your Q, When I integrate over all space, I will get E is equal to, if you want I can write a simple equation, E is equal to Q by R squared into unit vector R, right? Right? But I hope all of you understand that electric and magnetic fields are imaginary quantities, right? They are not something that I can measure. What do I measure in the lab? I measure Coulomb's force law, right? I can only measure forces between objects. I have two charged objects, Q1 and Q2, and the force between them is given by Coulomb's law, and we write the force is equal to, what is the relationship between the force and the electric field? The electric field is the force on the unit charge, but nature doesn't give us unit charges. Nature gives us electrons, protons and maybe quarks, but not unit charge, right? I hope you realize that a unit charge is a huge quantity. Do you realize unit charge is a huge quantity? What is the electron charge? 10 power minus 19 coulombs. So if you had an object which was 10 power 19 times of that, so it's like a very, very large charge. So we don't have such charges in nature. So the electric field is a convenience. Same way magnetic field is a convenience, right? It's the forces that you measure. So forces are measured and therefore you talk about field lines. It's not as though there is actually a line drawn somewhere, right? These are all mathematical constructs which are convenient because you don't always want to talk about the other object, because force means I'm talking about another object. When I talk about the field, it is the field at one point. I'm not worried about where the other object is, right? So these are conveniences and therefore I have converted this equation to this equation. And he actually had an integral form. That's, in fact, I was wondering whether that this is something that is, so how do you convert the left hand side to an integral form? So I say that here I have a volume V. So let me draw a volume V. This is my volume V. And let us say that the charge is located somewhere here. It's concentrated around the point x prime, right? So this is the, let me think of one point x prime over here. And it's the electric field due to that charge is here. This is E, right? And if I now want to integrate it, I define at this point, I define a normal and I say that this is theta with respect to that normal, right? So then what do I get? I get the normal component of the field. So this is the field, which is just Q by R squared, right? The magnitude of the field is Q by R squared. So Q by R squared into cos theta, because E dot n is just cos theta. So the perpendicular component of the electric field on the surface, so this is the surface S, is simply Q by R squared cos theta, Q by R squared cos theta, right? Now I say that I want to look at the field in a little surface dA. I want to sum up over all this whole surface, right? So I want to sum over this surface by integrating over this little dA. But how do I understand this dA? Let me write dA like this. Suppose I have in 2 dimensions, if I have an arc of a circle, then this is theta, and if this distance is L, let me call this distance as L and the distance from here as capital D, then theta is equal to L by D, right? Now if I write this in for a little segment of area, then this will be called the solid angle d omega, and if this distance is D and this area is dA, then d omega is equal to dA, maybe since I've used R over there, I'll use R over here, by R squared, right? This is a normal area. Now I don't have a normal area, I have something which is at an angle theta to it, right? So then this will now become dA cos theta, right? So you can see that dA cos theta by R squared, I can write it as equal to Q d omega. Now I integrate both sides. What is integral of the solid angle? 4 pi, right? So this is, of course, if it is outside, if the Q is outside the sphere, I will get 0. That's what Gauss's law tells me, right? Now what do I do to the left hand side? So now I have, this is called the first integral form of Maxwell's equations, E dot n dA over the surface of this volume is equal to 4 pi times the charge contained in the volume that it encloses, right? How do I get a differential form of this? I'm only giving this in detail. After that I will just say, oh, similarly, okay? So we are doing this in a little bit of detail. So how do I convert this into a differential equation, huh? Yeah, I use Gauss's theorem which says, see, I just don't know, there may be some quiet people who don't know this, so I don't want to, because they're quiet, I don't want to miss it out. So what does Gauss's theorem say? That if I have a function del dot f over some volume d cubed x over a volume v, then I can write it as the surface integral of f dot n over that surface area, right? So now I'm going to apply it backwards. So the left hand side now will become del dot E d cubed x over some volume is equal to 4 pi rho d cubed x over the same volume, and therefore if I look at the integrants, because I can bring it to the other side and the volume element is not 0, I can say del dot E is 4 pi rho. So for those of you who have seen the equation in MKS, you would get rho by epsilon naught, right? This is in natural units because I don't want to have epsilon naughts all over my equations, okay, or mu naught for that matter, fine. So this is the first equation, and we just got it by looking at distribution of a localized charge, right? So maybe we will put it somewhere over here. Del dot T is equal, so okay, so then what do we do? Shouldn't have rubbed off this equation. Let me just keep it. Always, it's nice to write equations where you can see, right? So suppose now I have a static magnetic field. How will I write B of x? Just by looking at that equation. Similar, right? Again, B is, what will you write? Instead of rho, what will you write? Very nice. So you will write J of x prime, and because that is a vector, you will write cross x minus x prime by, it's a 1 by r squared law, right? See, this has a dimension 1, so if I make it a unit vector, it is just 1 by r squared, right? And by the way, this in my units, there is a 1 by c. See, these units you have to just fix somewhere, okay? And you hope that the textbook got it right. Okay. So how do I get the second Maxwell equation from this? Can anyone see? I have an A cross B, and do you know the property of, what is this a function of, the right hand side? What is it? What is the right hand side a function of? X, right? Everyone, x prime is a dummy integration variable, right? So it is a function of x, but the integration variable is x prime, right? So it is not integrating over x. So can you see that the derivative of 1 by x minus x prime is exactly minus of this quantity, right? So I can write this as there's a minus sign, it's not del prime, it is del. Del means it acts on x and not x prime, and I hope you can see that del prime of this is minus del of this, because this is x minus x prime, right? So if you act del on this and if you act del prime, it will act on this, it will give you minuses of each other, right? And I can remove the minus sign by putting, right, del is acting on, right? Now this j is a function of x prime. Only del has x minus x prime, right? So I can write this as because it doesn't care about this, right? Sorry, cross. Clear? From this immediately, how do I get second Maxwell's equation? I can hear people saying something, but no, because the left hand side is just b of x, right? Very nice, just take the divergence, right? So I have b of x is equal to, so let me write it schematically. I have b is equal to del cross of something, which is just a number, right? It will just be a function of x. So I take the divergence on both sides. Let me call it f of x, it doesn't matter what it is. Why is this 0? Why is this 0? Always del dot del cross is 0, right? Right? I hope, by the way, that you know how to do these cross products in terms of epsilon ijk, and you are not writing matrices. Sorry, this is an aside. When I write, well, let's not take a and b, not even x and y. Give me some variables. Not r is the distance. S and t, okay? Let's take s cross t. Okay, so how do I find the element? Let's take 3 dimensions. Let's not worry about 4 dimensions. We are still dealing with del in 3 dimensions. How do I take a cross product of 2 quantities? Let me say that I want the I goes from 1 to 3. I want the ith component of s cross t, that can be written as epsilon ijk sj tk. Has everybody seen this? Because when we write it now in 4 dimensions, otherwise you will, not be able to do any of these calculations, right? Fine. So you can use this to prove this equation extremely straightforwardly. So now we have, fine, and therefore we can write B is equal to del cross A. So this whole thing will just become A, right? Because del dot del cross A will be 0, and that will satisfy del dot B equal to 0. That's how you get your vector potential, right? Fine. So this is okay? Now what are the Maxwell's equations that are left over? Yeah. So I have to get I have got del dot of 2 things, now I have to get del cross. Let us start with del cross B, because we already have the expression for B on the board, right? So I am going to write B is what? B is that object over there, right? So now I have to find del cross B. So that is 1 by C del cross. What was B? B is del cross J by x minus x prime. Integral d cubed x prime. And in fact, I could have put the integral. Let me put the integral here, because del is outside the integral, right? So what is the formula for del cross del cross? So, okay, I think at this point I should give you 3 minutes to just derive it in your notebooks, right? Use this formula, so you will have del cross S. So first you write del cross S, ith component in terms of epsilon ijk, or write the jth component, and then from there, so this then you call this as some t, so then you find del cross t ith component. Okay, will you please do this and see what you get? So this j prime just means j of x prime, okay? I'm just being short with my notation. Okay, shall I move ahead? Is that okay? That this is the formula that I wrote on the right hand side? Okay. Now I already told you that del acting on this denominator is the same as minus del prime acting on this denominator. Okay. And I'll put a bracket here because now I have to be a little careful. Why should I be careful? Because now this is d by dx prime and this also contains x prime. But right now, because this was acting on this quantity only, it is still only acting on that quantity. I have not done anything else. Okay. Then now what I will do is I will do an integration by parts and convert del prime to act on j. So I will get plus del of del prime dot j prime x minus x prime. Okay. What is this? J prime is independent of x. So this is simply del squared of 1 by 1. Write it here. What is del squared of 1 by mod of x minus x prime? Has anyone seen this before? Huh? Yes, it is the Dirac delta function, right? No one has seen this before. How did you do this calculation in the class? Okay, fine. If everyone is looking blank, so let's forget x minus x prime. Let's just call it x. Okay, then we can always shift the origin to x minus x prime. So what we want to show is that this is equal to delta cubed function, so function of x minus x prime, right? So the way to see it is like this. Let us start with r is the magnitude of x, right? What is the divergence of 1 by r? Can you quickly calculate it? What is r? R is root of x squared plus y squared plus z squared, right? So let us just think of it. You always think of the one variable thing, right? So 1 by root of x squared plus y squared plus z squared. And you're doing, let us write d by dx of this. How will you get d by dx of this? Just d by dx of something to the power of half is half, something to the power of, so this is like d by, let's look at d by dx of something to the power of minus half, right? So it will be minus half, something to the power of minus half minus 1. So this will be r cubed, right? And then the derivative of this object, which is 2x, right? And so the 2's will cancel, and so you will only get, it's a vector quantity, you will get r by r cubed. Is this clear? Everybody understood this? No? Is it okay? Okay? Fine. Now, you can see that once I have a 1 by r, if I take x equal to y equal to 0, then this whole thing blows up, and therefore there is no meaning to the statement unless r is not equal to 0, right? So you can see this immediately that the non-zero quantity is only coming when r is equal to 0. When r is not equal to 0, you have only this quantity. Now I have to do one more del on this, right? So when I do one more del on this to get del squared of 1 by r, Now there are two quantities. There is R dependence in the numerator and denominator, and please do it as homework. Again we will take R not equal to 0, but when you do all the calculation you will get 0. Is it clear? You have to do this. It will be some 3-4 steps because you will have to differentiate numerator, denominator, use various rules of differentiation, but when you add them all up you are going to get 0. Just explicitly you are going to do this. So take this result and do one more del on it to get del squared of 1 by R. So how do you deal with the quantity at R equal to 0? What you do is that you take the integral over some volume, finite volume, and this finite volume must include the origin. So it can't be any arbitrary volume, but it is some volume that includes the origin. Then what is del squared? I can write this as del dot del of 1 by R dV. Now I have rubbed it out, but you know that integral over a volume of del dot f can be written as f dot n dA, right? So this will be integral over the surface del of 1 by R dot n or dot dA, whichever may be dot n. I have been using dot n dA. But what is del of 1 by R? Here minus R by R cubed, right? That is equal to minus R by R cubed dot n dA. Now what is the little volume element in 3 dimensions? Yeah, d cos theta d phi, right? So if you don't know d cos theta, sin theta d theta d phi, right? So I can remove, just call it a unit vector and make it r squared. So the r squared will cancel. So I'll be left with only cos theta d phi, which is the solid angle d omega, which will give me 4 pi. Right? And this contribution is coming from the origin, because you know that it is 0 everywhere except at the origin, right? Because we have always taken this to be 0. So if you want this equation and this equation to be consistent, then the entire non-zero result has to come only from R equal to 0, and therefore you have to put the delta function. So when R is not equal to 0, so this will be, you will read it as d cubed of R, right? Because I have just done of R, right? I mean, you can convert everything to R minus R prime, it will be the same result. So you can see that when R is not equal to 0, then the answer is 0, which is exactly what we have got over here, right? When R is not equal to 0, the answer is 0. But when R is equal to 0, then this will become 1 and the answer is minus 4 pi. Is it clear? So this is therefore minus of minuses plus 4 pi. I have integral j of x prime delta of x minus x prime d cubed x prime. Is it clear? So what is j of x prime delta of x minus x prime? I hope the delta is clear. It's a delta cubed. It means delta of x minus x prime, delta of y minus y prime, delta of z minus z prime, right? It's a 3-dimensional delta function. So what is in 1 dimension f of x minus x naught delta of, or let's write f of x delta of x minus x naught dx when the volume element contains x naught? What is the answer here? F of x naught, right? So the same thing in 3 dimensions, this will just be j of x, right? Clear? Clear? Is it okay? Fine? Okay, so this part we have got. Now we have to still deal with this first part. What do I have to say about it? Okay, so now we have two solutions, okay, and I would like to split it into two parts just in the interest of not deriving all of electrodynamics all over again in 2 days, okay. The first solution is that I have here del prime dot j prime, okay, but we know that in steady state magnetostatics del dot j equal to 0, steady currents, right. So let us just solve that first, then we will put Ampere's displacement current afterwards and correct for it. So what will happen? You will just get del cross B is equal to 0 plus 4 pi j. Actually there was a 1 by c, so I should get a 1 by c j. And it will be easier to correct for j, the displacement current, rather than to solve this integral when del dot j is not equal to 0. That's why I already showed you the continuity equation. What is wrong with del dot j equal to 0 in the general case? What was my continuity equation? Del dot j will be minus 0 by dt because I had d alpha j alpha equal to 0. So del dot j is not 0 in general, but it will be related to minus 0 by dt. But what is minus 0 by dt? Minus 0 by dt will be related to d by dt of del dot e. And there's a del dot here, there's a del dot here and the del dot there. So I can write it as del dot of j plus dE by dt. So that is my Ampere's displacement current. So now that if you can see it immediately, let me just write that down and be done with that equation. So plus, so there will be that 1 by c sitting because you are substituting here, or it will not, yeah, dE by dt, right. So now we have remove all this. Okay, I think what I will do is, so let me just write it here first. So del cross B was 4 pi by c. So you can see that in this form of writing my elements of j alpha are rho and j by c, okay. But you have to just have a consistent set, right. So this came from writing del dot j is minus d rho by dt and substituting d rho by dt as del dot dE by dt, right. That's what you get. So this is the modified Ampere's law by Maxwell, which poor thing, he just did one thing and but everything is now called Maxwell's equations, right. So now the last one has even more complications. So I'm just wondering, okay, I will just give an outline of the equation and I will leave it to you either in the tutorials or if you think you know it, you can forget about it. So what is left over is the final equation for del cross E, right? Sorry? Right, so where does this come from? Faraday's law. So we have to talk about time varying fields. This is exactly why those equations were not enough and we had to add this portion, right? So what does it say? That if you have a changing magnetic field or a coil current which is essentially a changing magnetic field, then you generate an EMF, right? And that EMF is then proportional to the flux which is linked with the circuit, right? So what is the flux? Flux is given by, so it is related to the time change of the flux which is B dot A, right? So B dot N dA. So over the surface of the circuit. Now you can see how abstract these concepts of E and B are, right? Because it's not as though there is a physical something there. You're integrating over some circuit which can be anything, right? Now you have to do many things. You have to write d by dt as partial d by dt plus v dot del. Has everybody seen this? If the motion is with a velocity v, why? Because if you have some function of x and t, then d by dt of this is d by dt into dt by dt plus d by, I've taken only one dimension, into dx by dt, dt by dt is 1, so that is d by dt plus dx by dt is the velocity, and if I take 3 dimensions that becomes del, right? Is it clear? Fine, so I have to account for this motion part, okay, and then I have to do many things, and I don't think I will do the many things. Okay, let me just write outlines of the equations. So I will get a line integral of E dot dl, okay, and that will come out to be minus 1 by c d by dt of this b dot n dA, which I have written on the top. Now I use Stokes' theorem to convert this into a del cross E dA, right? So now I've written always dot n, so my area element has no this thing, is minus 1 by c d by dt of b dot n dA. Then I can actually write del cross C is equal to minus 1 by c. Sorry, this will take longer and I don't want to spend that much time, so I kind of fast forwarded it, but I've told you where it comes from, okay. So this essentially tells you that when I have a changing magnetic field, what did Faraday find? When he moves a circuit or switches on or switches off the current in the circuit, or he brings a magnet close to the circuit, then an EMF is generated in the circuit, and that is the EMF. So it has to be time changing magnetic field, and therefore it is related to dB by dt. So dB by dt comes because you have time changing magnetic fields, dE by dt comes because you have time changing current charge densities, right? That is the source of these two terms, and this is the Maxwell's equation. Sorry for fast forwarding, this is a little bit long derivation. So maybe someone who wants can ask for it in the tutorial, right? So I want to move on from there. So we have our 4 Maxwell's equations. So maybe I should say a few words about them. So the two equations, del dot B equal to 0 and del cross E. Can you see? Actually, I don't need to, I have not written it in the right order. Okay, I will write it again. These are the two homogeneous Maxwell's equations, and del dot E is equal to 4 pi by C. Either it is 4 pi by C or rho by epsilon naught, I don't care. And del cross B is equal to 4 pi by Cj plus 1 by C. Let me write it the other way. Minus 1 by C dE equal to. These are called the inhomogeneous equations. That's basically the right hand side here involves the charge and current density distributions. In the other one it is 0. So they are the homogeneous solutions. Okay. Then maybe I should simply also include over here when I am saying all this, we have B was del cross A, that doesn't change, but because of that extra piece, E was minus del phi for static fields minus 1 by C dA by dt. That comes from that extra term that we have got. So you can substitute these quantities and check your definitions, okay. So then I can write my electric and magnetic fields in terms of the scalar and vector potentials. Now you have to notice one thing, the relationship between the B and E fields, ultimately these are related because Q times E is the force, right? So these are ultimately related to the observables, are related to first order derivatives of the potentials, either the time derivative or the space derivative. Which means that if I add constants, either time independent or space independent constants appropriately to A and phi, the E and B fields will not change. That means I can only determine A and phi up to these constants. Okay, so there is a certain arbitrariness in A and phi, and you will have heard of this as something called a gauge transformation or a gauge fixing. Okay, so all it means is that because I can add things to A and phi and not change. For example, if I, you know that, okay, let me give a specific example. So because of this, there is an extra freedom in this definition of A and phi. But before I go to that freedom, let me just, you can substitute over here, you can substitute for E and B in terms of the A fields, which is A and phi fields, and I will just get out of the way the fact that when rho is equal to j equal to 0, I hope I have written that equation somewhere, yeah. So you can see, when I substitute, for example, del dot, del phi will give me del squared phi and so on. So I will get things like minus del squared phi plus 1 by c d by dt of del dot A is equal to minus 4 pi rho, then del squared A minus 1 by c squared t squared A minus del so I have just substituted, okay, you can just substitute. I copied it because I didn't want to make mistakes. Okay, now this contains A and phi and this contains A and phi. So there are two sets of coupled differential equations which I want to decouple. So what do I have to do? I have to substitute something somewhere. So first thing I do is that I shift A, so A is a vector A, to A prime. This is not a Lorentz transformation. Now this is simply a gauge transformation, and the reason I can do it is because I do have that freedom in this definition. Simultaneously I shift phi to phi prime, sorry, A goes to A prime, which is A plus del lambda, phi goes to phi prime, which is phi minus where is the c, sorry, 1 by c d lambda by dt. So you can see immediately, for example, the extra term will be del cross del lambda. Del cross del is 0, right? So the extra piece that you have added is 0. Same way here you have had it. So here you will add d by, okay, here you will add d by dt of del lambda, here you will add del of d by dt of lambda, and the two terms will cancel each other, right? So E and B will remain the same E and B. But you see what happens to this extra piece over here. This extra piece becomes 0. So I will have 1 by c d phi by dt plus del dot A. C dt is x naught, del is x1, x2, x3. So this is simply d alpha A alpha is equal to 0. Suddenly I have brought back my 4 vectors, but you can, otherwise you will never remember what this is. You will remember it because of this, right? That is the power of this 4 vector notation. So with this constraint, this goes away. This becomes an equation only for del squared A. Then you can solve it and substitute back here, because now del dot A will be related to minus 1 by c d phi by dt. So when I put del dot A as minus 1 by c d phi by dt, this will become 1 by c squared d squared phi by dt squared. These will become identical equations, and these are the wave equations. Can you see that? So you have 1 by c squared d squared by dt squared minus del squared of either A or phi will be equal to 0. And you can, I hope you all know that these are wave equations, right? Let me write it down once more. So if you substitute, you will get both the equations will come to be 1 by c squared d squared by dt squared minus del squared of either phi or A, doesn't matter, equal to 0. So for example, phi will be equal to e to the I k dot x minus omega t. This is the wave number, this is the omega frequency, h cross omega is the energy, and k by omega is the velocity, which will here be c. If you put back mu naught epsilon naught, you will get C is equal to 1 by root mu naught epsilon naught, okay. So this is your wave which is traveling at the speed of light. A will also have, so this is, let us say this is phi naught times something. A again will be A naught times same thing, okay. So that means when in the absence of external charges and currents, your Maxwell's equations are actually, the solutions of Maxwell's equations are just electromagnetic fields which are waves which are traveling at the speed of light, which I will not derive here, but you have to just find what is the omega by k relationship, you will get C, and then therefore this is the electromagnetic wave that people talk about, right. If you can also replace back in terms of E and B, you will also find that E and B are waves. So you don't have to say that they are waves only in A and phi, it's a little more algebra, but you will find E is also E0 e to the I k dot x plus minus omega t, and B is also the same thing, only thing they will be perpendicular to each other, that's why they are called transverse waves. So the phase difference between the E and B field will be 90, so that when one is maximum in x, the other is maximum in y, when they are propagating in z. So this is a completely transverse field, okay. So all this I see that I cannot repeat all of this, but this is the highlights of what is important. So this is the wave equation. I can write it either in terms of A's or I can write it in terms of E and B fields also. And these equations now are important because I want to then find the manifestly Lorentz invariant version of these fields. You can see that, right? Already I have, you can see this, I have already got, because of these two equations, what is this? This is the 4-dimensional gradient, Laplacian, right? It is called box. Just like del squared is d squared by dx squared plus d squared by dy squared, which is called with a triangle, which is 3 dimensions. So this is called a box. Some people write box squared because it's like del squared, but people also write box. So you can have box of phi equal to 0, a box of A equal to 0, and now I know phi and A are actually components of my 4-dimensional vector potential, not vector potential, 4 vector potential A. So this becomes box A mu is equal to, and if I bring back that thing, I will get box A mu is equal to, I've been using alpha, so box A alpha is equal to J alpha. Nice, right? It looks so nice. Now, no, just throw away all your Maxwell's equations and remember like this, okay? But we still have to write F alpha beta because we don't know the relationship between this and the electric and magnetic fields. So we will keep going, okay? We have some more distance to go, but you see that it will get extremely simplified. So on this page, do I want to say something more? Okay, fine. Now, even though I have defined a gauge transformation, this is, by the way, this is a simultaneous gauge transformation. I have to simultaneously change both. Otherwise, if I change only one, either E or B will not be invariant, right? So this is a simultaneous transformation, but there is still a residual freedom in this. And the residual freedom is because you can see that this satisfies or you just have to do one more derivative and you will get this, okay. So I have introduced a completely arbitrary term lambda, some function, it's some function of x and t. I have added the gradient of that to A, I have added the time derivative of that to phi, such that I get this condition. And where do I get this condition from? I get this condition from the requirement that if I start out with d alpha A alpha equal to 0, I must remain with d alpha A prime alpha equal to 0. And this box lambda equal to 0 will satisfy that constraint. You can see that that also looks like a wave equation for lambda, right? Somebody, I don't remember who asked, you asked me this question about gauge invariance is a very different thing, okay? Gauge invariance will come in field theory. Here we are just saying that we are using the fact that there is freedom because your potentials are defined such that only derivatives of the potentials appear in E. So when I integrate these equations, when I integrate a d by dx, I get something plus constant, right? So those, I can always fix those constants appropriately. They will always be unknown or up to those constants. Only when I measure the physical E field I can fix that constant, right? So because of this freedom, I can have a gauge choice. So this particular gauge choice is called the Lorentz gauge. There are many gauges that you can use. This gauge people like because it is manifestly Lorentz invariant. It's called Lorentz gauge. But the other thing is that you can use non-Lorentz invariant gauges also. The main thing is that you have this residual freedom which you can fix, and therefore there are two sets of constraints. So there is one set of constraints here, and then there is this second set of constraints here. Now there is some little bit of algebra still to be done, but I will give you roughly the interpretation. We know that the solution of these wave equations is that you have a transverse wave where the E and B fields are mutually perpendicular to each other and also transverse to the direction of motion. The direction of the electric field vector is called the polarization of the electromagnetic field. So you know that it has polarization in the x direction or y direction. If I take x plus Iy or x minus Iy, I get left circularly or right circularly polarized light. You know that light can be polarized, right? So the electric field vector is what is the polarization vector. In fact, if you take the Fourier transform of the electric field vector, that is actually the polarization vector. That E itself is the polarization vector that will give you the direction of spin or whatever the polarization of that object. Okay. Now what happens is that because you have a transverse wave, the photon is a massless particle. I am now making just statements. I am not going to show you any of these things. It has only 2 degrees of freedom. It can have spin. Suppose it is moving in the x direction, it has spin, that is the electric field can be in the x or it can be in the y. Now we had a wave equation which had 4 components, right? It had phi, ax, ay, az. But the degrees of freedom for a transverse wave are only 2. And this gauge conditions therefore and the subsidiary gauge conditions remove these extra degrees of freedom and make sure that you have a transverse wave which has only 2 degrees of freedom. Is it clear? So this is why it's not an accident that this happens. It happens because you actually have a massless transverse wave which actually corresponds to an electromagnetic particle called photon. I mean, when we do quantum mechanics, it gets quantized E is equal to h nu, right? So that is the photon wave packet, but it will still remain transverse as a wave, and therefore that 2 degrees of freedom will go away. And you will see it later when you talk about quantum mechanics or relativistic quantum mechanics, that this massless particle which has only 2 spin degrees of freedom, therefore will have to have 2 constraints to remove the other 2 degrees of freedom. Okay. So far I have only talked about these inhomogeneous equations. These homogeneous equations we keep forgetting, but we will come back to them later, and I will actually take it up in the next class. So this is, I went slower than I thought. I think I will, since I have said so much, I will talk about some more Lorentz invariant quantities. I will talk about energy, I will talk about the Poynting vector. I think that for people who have not seen electrodynamics, I don't want to leave it in half. I will apologize to all those of you who have seen it before, but I will complete at least. So what I want to show you is that the electromagnetic wave is actually a genuine object. If you can think of it as a particle, because it has energy, it has momentum, it has angular momentum, and there are conservation laws for all these. Just like you have in mechanics, classical mechanics, even if you take Newtonian mechanics, energy, momentum, angular momentum are conserved. The same thing you can define quantities for the electromagnetic field. It has energy, it has momentum, it has angular momentum. Okay, and these quantities also, it's good for you to see what they look like, because they will all be in terms of E and B or in terms of J. So let us look at all of them, so that at least some completeness will be there. So tomorrow maybe I will just spend some 20 minutes or something like that on completing this. Yeah, I think that it will just take some 20 minutes to do that, and then after that we can go back to writing all of it in terms of our 4 vectors and tensors. Okay, and that will only be tomorrow. So in the last class what I will do is I will actually do a Lorentz transformation. So I will take a point charge at rest in one frame, and then I will move it to a relativistically moving frame, and let's see how that looks in the 2 frames, and then I will finish over there. Okay.